Hello friends, in the last class we looked at the motivation for the course. We also looked at what do you mean by efficient algorithms. So we looked at how to model efficiency. The model is through the concept of big O notation. We saw precisely the definition of big O notation. We also looked at few examples of how to determine the complexity, or how to precisely determine which order the algorithm is. Today we also observed last time or mentioned is that one of the key factor in translating an algorithm into a program are precisely how are the data that we handle for that particular program is going to be represented on a machine. So before we actually now look at applications and try to find solutions and write programs for them, we spend a session where we look at how this data that we want to handle is going to be represented on a machine. So today the lecture is going to be more concentrated on looking at data to be represented and what sort of structures or models that are available to us. Again, it is not difficult to imagine that different applications will require different type of data and different type of representations which are suitable for those applications. So today we are going to concentrate on a variety of data structures which are used for representing data, try to see for what applications we can use them, try to see advantages, disadvantages, and then later use them in applications. So the agenda today is to look at data structures and try to understand, try to see how they are going to be represented. Yeah, so before we move over to individual data structures, we will try to abstract them and see what are the common things that each of this data structure is going to have, common in terms of what we are going to do with them. So that is what an abstract data type would mean. So it is a mathematical model for a class of data structures that have similar behavior. In the sense, typically as we know, data that we handle or the way we are going to represent is going to have commonality in the way we are going to operate on it, and abstract data type would try to capture that abstractness. So once we know in general to work with abstract data types, we can as well move over from abstract data type to data structures. So abstract data types basically looks at what operations that you are going to do on those data, but does not worry about how one is going to achieve it. So it basically hides the implementation details from the user. So abstract data type allows user to use only what he wants from the representation, rather than worrying about how a particular fact is going to be implemented. So an abstract data type is independent of the implementation. So what are the typical operations that we do when we work with data? Right? It can be a database for a particular university, a student database. We know typically we are going to add data to a database. If you have new students, new batches coming in, you would like to add their IDs, their preferences, their credits, units, whatever to the database. So typically one of the most common operation that we do with data is we add more elements to the data. Similarly, if somebody passes out from a university or a college, his data needs to be deleted from the records. So the two most common operations that we do with data is addition to the data and deletion from a data set. Also many times we like to inquire about the data set. We would like to find a particular student ID and see how his performance is. And so these are the three typical operations that we do on a data set: add, delete and query. So that precisely are the three things that are being said here. So you can add data to data collection, you can remove, or you can ask, or you can query the database. So data abstraction allows you to help only about what you can do with the collection rather than worrying about how to do it. That's what we already said, is that abstraction allows you to worry only about what we want to do rather than how we achieve it. It allows us to work with data structure without worrying about the rest of the solution. So it allows you to work in isolation. The simple abstract data types that we are going to use, or we are going to try to look at, are stack, queue, vectors, list, sequences and iterators. So these are a few of the standard simple abstract data types that are used in practice. So in this particular course, we are going to concentrate on stacks, queues and linked lists. So in this particular session, we are going to discuss about the three marked things that are on the screen, that is stacks, queues and lists. The details of the others can be found in the reference book and can be learned, but they are not going to be much used in this particular course. So I am not going to concentrate on them, we are going to concentrate only on stacks, queues and lists. All these lists that we have put down here are part of what are called linear data structures. Again, we know from our experience of doing applications is that the data that we deal can be of two types. One is there can be relationship between data which we would like to represent, which is typically used in hierarchies in organizations where two employees can report to the same boss, or more than two employees can report to the same boss, and we would like to capture this relationship when we want to represent data. Or when we are doing with applications like sorting numbers or searching something in a sequence of numbers, the relationship between the data is not essential or is not present to be captured. So when you don't have a relationship between the data items that we want to represent, we use these particular structures which are called linear data structures. We also, as we go ahead, look at how to represent data which is going to have relationships between them. That will lead us to what are called non-linear data structures that probably would follow as we finish this particular session. So the first data structure that we are going to look at is called a stack. So the closest analogy to stack, as the name indicates, is a stack of plates in a kitchen room. Right? So as you get newer and newer plates, you keep on adding them at the top of the stack. Like so, for example, if you have a stack of plates like this, and a new plate has to be added, you are going to add it here at the top and not at the bottom. It just is more efficient to add more plates to the top of the stack of the plates rather than trying to add them at the bottom of or in the middle of a stack. So that precisely is the analogy about stack. So you keep on adding data at the top of the stack. The policy that it follows can be called as what is called the LIFO policy. That is last in, first out. That is the element which is going in last is going to come out first. We also know that if we want to remove plates from the stack, we usually would remove first the topmost plate, then the next plate and then the last plate. Again, it is for the ease of doing the operations, or the operations are more natural. If one decides, one can obviously try to remove a plate which is in between, but then we know it is not a natural way of doing things. A natural way is to pick up the topmost plate and remove it. So LIFO policy is last in, first out. That means the element which was inserted last will be removed first. So you can insert objects anytime during a correct. For example, in this particular example, when we are trying to add, so after adding 3 elements to the stack, you can actually remove 1 element from the stack, and the stack would look like this, and then we can add 2 more elements to the stack. So we can add any number of elements during the operations on the stack, but we can only remove the one which is inserted the last. These typical operations of insertion and deletions are called push and pop in stack terminology. So when we say we want to insert an item into stack, we will say we are pushing an item onto the stack, and we want to delete an item from the stack, we say we want to pop an item from the stack. It matches precisely with the analogy that we have with stack of plates, or you have a coin dispenser where as you keep on adding coins to the dispenser, you add it at the top, and the one which is added last is removed first. So it precisely matches with the understanding that we have from our natural way of looking at things. So as already said, the analogy can be with coin dispenser or can be with a stack of plates. Let us see now how we are going to implement this. Typically, as we said, we are going to be only interested in the operations that we can do with the stack. But finally, if you want to write down programs, you need to look at how you are going to actually implement this data structure. And so let us look at how this data structure stack is going to be implemented. The first way that we can do is by using what are called arrays. So we are going to create, if we have a stack, using an array by specifying what is the maximum size for a stack. So if you want, also that is the way we work in practice, is if you are trying to put items one on each other, typically we have a limit up to which you can add. After that, maybe your pile doesn't remain steady or whatever. Right? So you typically always have a last sort of, or as a upper bound on how many elements you can add to a stack. So if you want to implement stack using an array, first you need to specify the maximum elements that you want to add to a stack. In practice, probably you may not add, but you need to specify that number to begin with. So a stack would contain then an n element array. The indices start from 0 to n minus 1. To perform the operations of push and pop, that is insertion and deletion, at each instance we should know at what place is the top of the stack. So we need a pointer or an array as an index, which we are going to call t, which is always going to return what is at the top of the stack. When I say it is going to return, means it is going to return the index of the array at which the last element has been inserted. Right? So if I look at the picture here, the last element inserted is here, and so the top is pointing or is marking that particular index. So that allows us to know if you want to add elements, then it has to be added here, and if you want to pop an element, this element has to be popped. So an array implementation of a stack requires an index or a pointer, which we are going to call as the top of the stack, or and going to be represented by t. Since array indices start at 0, we initialize t2 minus 1. That is the initial condition when your stack initially is empty. Yes, so let us look at how the stack are implemented. So we will look at the pseudocodes for this particular implementations. If you recollect, pseudocodes are combination of natural language plus high level programming languages, so that it makes us easy to represent the procedure without worrying about the syntax of programming languages. So the functions that we are going to look at are follows. The first function that we are going to look at is going to be the size of the array or the stack. if you want to insert objects onto the stack, naturally you would first like to know whether there is space onto the stack or not, and this would be precisely given by the size of the stack function. So, it just returns the pointer called t plus 1. That means, if t plus 1 happens to be n, then we know the stack is full and you cannot add anything to it. Right. So, the function size tells you what is the size of the stack, which allows you to decide whether you can actually add more elements to the stack or not. You also have a function which checks whether the stack is empty. This is useful typically when you want to delete items from the stack. So, if your stack is empty, then there is nothing to delete. So, on an empty stack, if you want to do a delete operation, that should give an error message. Similarly, you need to know where the top pointer is. So, that is written by the function algorithm top. Now, let us look at the two main operations that we want to perform on our stack, that is push and pop. Push and pop, you recollect, corresponds to insertion and deletion. So, we want to push an element O onto the stack. So, the first thing that we want to check before you push is what is the size of the stack. If the stack is full, that is if size is n, which has been prescribed in the array implementation, then we cannot add anything to the stack. So, that is the first thing that you check, is the size of the stack n. If it is n, then it has to return error. If not, then if I look at this particular example, if I am going to look at t, if t is equal to n, then the stack is full and you cannot add anything to it. If not, you update the top pointer to t plus 1 and simply insert your element O there. Right. So, this precisely is the pseudocode operations or the pseudocode is doing. It looks at the top of the stack. If the top of the stack is not equal to n, that means the stack has space. It simply updates the top and insert the element. Now, let us look at the operation pop. As we already said, if the stack is empty, you cannot delete an element. That should return an error message. So, you are looking at, is the stack empty? If it is empty, then it is returning error. Else, we know the stack is not empty, that means there is at least one element onto the stack. So, you can perform a delete operation. So, in this case, what it does is, it will look at, simply what it is going to do is, it will return the pointer here. Right. So, in this case, it will return the pointer here. Instead of t, it will return the pointer to t minus 1. So, the stack would be returned precisely at t equal to t minus 1, and it will precisely return the index of that particular array element. So, pushing is precisely checking first size is full or not. If not, increment the top, insert there. In delete, first check whether the stack is empty. If not empty, decrement the pointer and return st plus 1. So, this precisely is the pseudocode for push pop into a stack. As we already observed that to implement stack as an array, we need to pre-specify the size of the data that we can handle, which is usually done using n. Now, if I look at the operations of push and pop here, let us see what is going to be the order of these operations, or what we are trying to find is for this algorithm how many operations are we going to perform. Now, if I look at say push and pop, we are going to first call this function. This is we are not going to check because this is a function call. What we are going to do is simply look at t equal to t plus 1 and assign the O to the location t. So, we are doing precisely two computations. One is incrementing the top and assigning 0 to that particular location. If you look at this, this is independent of the elements that you have onto the stack. Right. So, whatever number of elements you have onto the stack, you have t in hand, or you hold over t, you simply check t equal to n. If t is equal to n, we know there is an error. If t is not equal to n, increment t, insert there. So you are doing precisely two operations, which is independent of the array size, which is n. Exactly the same argument is for the pop operation. You simply update the pointer to t minus 1, and that's all. So there is only one basic step or operation that you perform, is decrementing the pointer, which is again only 1. Right? So if you look at these particular operations, the number of steps that you require to perform them are completely independent of the size of your array. And so precisely we say that these operations are performed in order O time, or if you recollect, we said order O, or it can be said it can be done in constant time, correct? Constant time would mean it is independent of the problem size, or it is independent of the size of the stack. That's the advantage, that is the operations that you want to perform can be performed very efficiently. But there are obvious disadvantages, that you need to specify your upper bound well beforehand, and it can happen that probably the size that you have already defined is too large for your problem. In that case, you are wasting a lot of memory, or it can happen that you realize after duration that the size that you have specified is too small, and then you cannot change your structure. So the major disadvantage is that you have an upper bound on the size of a array. Once you fix it, you are bound by it, whether you have that much data to operate or you don't have. If you don't have, then you are wasting space. If you have, or if you have more, then you cannot handle it. So though your operations are very efficiently done using arrays, there is a disadvantage of the size of array, which has to be specified well in advance. That brings us to the second data structure that we would like to study. How to overcome this particular disadvantages, we will see a little later, that how one can work or overcome this particular disadvantages. Yeah. So the second data structure that we look at are what are called queues. Queues we all are well aware of. I mean, most of us have been standing in queues at, say, bus stops, railway stations, ATM counters, banks, whatever. And queues are precisely the data structures which capture that notion of a queue. We all know that in a queue, if a person is added, he is added at the end of the queue, and a person who is serviced is at the beginning of the queue. And that what precisely is the principle on which the queue data structure also operates. The principle is in shorthand called a FIFO principle, that is first in and first out principle. Remember, stack worked on a principle called LIFO, which is last in first out, whereas FIFO is first in first out. And queue data structure precisely works as what the queues we understand in practice, in daily practice. So one can always add elements to a queue, but only the addition is always going to be at the end of the queue, and you can always delete elements from the queue, or an element which is at the top of the queue or which is at the beginning of the queue is the element that is going to be serviced. Correct? So elements can be inserted at any time, but only element which has been in the queue the longest, that is which is at the top, is going to be, or which is going to be at the front or beginning, is the one which is going to be removed. So unlike stack, which we required only one index or one pointer which was at the top, we need here two pointers, one for addition which is at the end of the queue, and for removal which is at the beginning of the queue. Right? So we are going to require two pointers which you are going to call them as rear and front. So I am going to have rear and front. So front is going to be as we see here, pointing towards the front of the queue or beginning of the queue, or pointing to element which is for the longest time in the queue, and rear is going to point to the one which has been last added to the queue or which is in the queue for the least time. Again, like data structures, there are two basic operations that we would like to do on queue. One is going to be adding an element to the queue, which we are going to call as enqueue, or we are going to or we are going to delete or remove elements from the queue, which we are going to call as dequeue. Then we also need functions like front and new. Yeah. So let us look at array implementation of a queue. So again, like stack implementation with an array, we need to pre-specify the upper bound on the size of the queue, which is done here. So you have to specify the maximum size for the queue. Already observe that what we need two pointers to keep track of adding and deleting elements from the queue. So we need a pointer or index called f, which is going to tell where the front of the queue is, and we need r, which tells us what is the end of the queue. So front and rear are going to be represented by f and r, which indicates the front and the end of the queue. Initially, before any elements are added to the queue or queue is yet to be populated, we are going to have the condition that front and rear are going to point to the same index, which is 0. So initially your array is going to be like this, and you are going to have f equal to r equal to 0. That is, this is at the beginning before any queue element has been added to the queue. So that is the initial condition. That also at any stage when your front is going to be equal to rear, the queue is going to be empty. Yeah. So let us look at this particular idea when f is equal to r. So let me look at this particular queue. Suppose I have 2 and 3. So f is 0, r is 2, r is pointing to this location. Now suppose you want to delete an element. Now if I delete an element, we know it has to be in the front. So what you do is you simply update your f, which is here. Initially recollect f is pointing here, I am just going to update my f here. So my f is now going to be pointing here. Now suppose I delete also 3. So your f is going to be pointing now here. So if you delete 2 and you delete 3, you will again have f equal to r equal to 2. That means your queue is empty. Right? So your queue empty condition is captured by the relation f equal to r. Right? So initially the queue is empty, that time f is equal to r, and they both point to the same index, which is 0. As you keep on doing adding elements and removing elements, at any stage if you have f equal to r equal to whatever index, that would indicate that the queue has no elements in it. Right? So that explains this particular condition, that f equal to r is going to be a condition which is going to imply that your queue is empty. That precisely is also the disadvantage that we have with working with this particular sort of queues. Correct? So what can happen is, if I have, so we have already seen this, if you have a queue whose size is say n, and I take a single element, let me call this as O, if I keep on inserting and deleting this n times, right? So what we are saying is, you are going to repeatedly enqueue and dequeue a particular element, then after n such operations you are going to get f equal to r equal to n, which precisely would mean that the queue is empty. The condition captures the fact that the queue is empty, but we know that we have been just playing with the queue by inserting the same element and deleting the same element. That means though your f and r are all pointing here, the queue is not storing any element, and you certainly do not want such a situation to arise, in which you have plenty of space into the queue, yet your Q looks to be full because your F is pointing to n. Remember, when F is going to point to n, this condition would mean your front is at n, would mean there is no space into the Q. You certainly don't want such a situation to arise. That means you want that the Q, you should be able to add more elements to it. So this problem is solved by using what is called wraparound. So you allow F and R to wrap around the Q. What that would mean is, once you are here, right, so that precisely would mean when you have F pointing here and you still have space into the Q, if you want to add and if you want to delete an element, your front can be wrapped around here. Or similarly, if you want to add elements and there is space here in the Q, then you can update your R to this. Right, so the problem precisely is solved by allowing your R and F to wrap around the Q. So the wrapped around configuration would look like this. So it can happen that your rear happens to be before your front. Right? That means rear is pointing to an element or to an index 2 and front is pointing to an index 10. But that situation can arise because you can have a series of, say, insertions followed by a series of deletions and so forth. And we seen if you don't allow wraparound, you will have enough space in your Q, but your Q would look like the Q is full and you cannot add anything else to the Q. So to overcome this problem, you allow what is called a wraparound configuration. The incrementing part just has to be taken care by doing modulo operations. So instead of just incrementing R to R plus 1 and F to F plus 1, you increment by doing these operations modulo n. So instead of doing F plus 1 and R plus 1, you do R plus 1 n modulo n and F plus 1 modulo n. That allows you to wrap around the Q. Yeah. Let us look at the simple pseudocode implement algorithms for the operations that we said we are going to do on the Q, that is NQ, DQ and the other operations that are going to support this particular operations. So what we need is the size of the Q. We said if the size of the Q is full, then you cannot do a NQ operation. If the Q is empty, you cannot do a DQ operation. So sign is simply you look at n minus F plus R and do modulo n. Okay, so you look at the size of the Q n, then you look at what is your front, what is R, add them, subtract it from n. Okay, so for example, if this is my size, so you have say 1, 2, 3, 4. So you have a size is say 1, 2, 3, 4, 5. So your 5 n is equal to 5 is the size. My front is here and rear is say here. Okay, so this is 1, 0, 1, 2, 3, this is 2. So my size of the Q is precisely 5 minus 2, which is 5 minus so the size of the Q is going to be 5 minus 1, front is at 1 plus 3. So which is 5 minus 1 is 4 plus 3, 7, modulo 2, modulo 5 is going to be 2, which is the size of your Q. Right? So this simple formula gives you the size of the Q. Let us look at the two main operations that we have, that is DQ and NQ. So DQing, again already said, if this Q is empty, then you cannot DQ, it returns an error condition. If not, it just look at the front of the Q. Okay, so if the front is here, it simply makes this as null and updates F to F plus 1. As we said, if you do a circular representation, it will be F plus 1 modulo n. So what we have done here is the circular implementation of the queue. So we are looking at circular queues and its implementation. If it was the normal queues, you would have just f plus 1 rather than f plus 1 modulo n. Similarly, your dequeue operation is going to be, you just look at if the queue is empty, then you cannot dequeue, otherwise simply, so if you look at the enqueue operation, you simply enqueue it at the end of the queue and simply update your rear. So remember, if you look at, you know, to be careful in remembering the fact that your R is always pointing to the index of the element after the rear one, or it actually points to the space where you can actually insert or where you can enqueue an element. R never points to the index of the last element, but to the next available space in the queue. Like this point has to be remembered when you write your implementations. So if you look at here, so when you are enqueuing, we know R is pointing, so when you are trying to enqueue, and if your R is pointing here, that means all these elements are already filled in, and so you can add an element here and simply update R2 here. Right? So you are inserting O at R and updating R to R plus 1 modulo n. Okay, we already seen the pluses and minuses that are there when you work with array. It's easy to check, I didn't do that, but like your stack operations, the queue operations, that is enqueue and dequeue, will also take constant time. And these all operations, if you just go back and check, doesn't depend upon what the size of the queue is. This is because you have in your hand the pointers R and F, and you are only playing with these pointers R and F, and that doesn't depend upon the array size that you have. Right? So like stack, your queue operations are also going to be of constant time. So they are good in terms of access, in terms of operations, arrays, but they are not so good when it comes to resizing them. And whereas we know many times in practice, we don't know how much data we are going to handle beforehand, and we have to keep provision for such sort of data which may later come in. So we need the liberty of resizing or the flexibility of resizing. And array, it may not always be available. So that is allowed by a structure which is called a linked list. Rather than array, you do what is called linked lists. So a linked list is a data structure. It consists of sequence of nodes. Each node contains the following information. It requires the information about the element that is going to hold. It can be number, it can be character, it can be anything else, whatever you want to represent. Correct? So every node is going to have what element it stores, and it tells you what the next node it is going to point to. So it gives me a link to the next node. So this precisely is, so it stores two things, the element, and it also stores a pointer which is called next, which tells you address of the next node in your list. Unlike array, which we know is a contiguous locations in the memory, in single linked list it may not be a contiguous chunk of memory. A node can point to another node which is not immediately next to it in the memory hierarchy or in the memory structure. So what you have is the link basically tells you, the link or the pointer next tells you the address of the next node in your memory. So if I look at this particular linked list, it stores whatever elements A, it stores address of the next location, and we indicate by doing this. So we point a pointer which is going to the next location. So in a linked list, if I look at a particular node, it has the following information in a single linked list: what data it stores and what is going to be the next node in my list, or the address of the next node in my list. In a single linked list, if you look at, there is a disadvantage in the sense that every node just knows what is the next node that it is there in the list. So that means you can traverse only in one direction. So if I look at traversal, your traversal is only in this direction in a linked list. That is, you can traverse only in one direction. At this particular node, for example, you are here and you want to go back into the list, then there is no information available at this point about this particular node. So that's a disadvantage with a single linked list, is that at a given node, you know only the next one or the next address. You don't know how you have reached there. Right? So there is no information at this as how you have reached here. So there is no possibility of going back here into the list. So to overcome this disadvantage, you do what are called double linked lists, in which now every node will have also information about not only the next one, but also from where it was pointed to. So it will also have a pointer which is called a previous pointer. So now it will have sort of three fields or three things to be remembered at a node: element that it stores, like single linked list, it's where it is going to point to, or what is the address of the next node. In addition to that, the address of the previous node. That allows you to go back into the queue and also allows you to go front into the queue. So it allows you the flexibility of going ahead as well as going back into the queue, which was not there in a single linked list. So in practice, many times we tend to use double linked list rather than single linked list for this flexibility. We also going to add two sentinel nodes to make things easy to operate. We are going to add two nodes, and header node and a trailer nodes, which are called sentinel nodes. They don't store any element or any data, but they just point to the first element of the list, and this points to the last element of the list. So for a header node, its previous pointer is going to point to a null point, is going to be a null pointer, and for a trailer node, its next pointer is going to be a null pointer. This header and trailer allows us to write things in a more natural way. It allows you to do implementation in an easy manner. So in practice, to a node, whether it is single linked list or a double linked list, we will add these two particular nodes which are called header and trailers, which are mostly for convenience, doesn't really help much in otherwise. So I am going to look at insertion in a double linked list. Insertion in a single linked list is just a particular case of insertion in a double linked list where you don't have the previous pointers. Right? So it's easier than that, so I am not going to try to work on it. I am just going to try to see insertion in a double linked list. So as you said, advantage in a single linked list is you can insert it anywhere in between. Correct? So suppose we want to do an insert after a particular node. Correct? So you have to insert after P a node which is going to carry a value x. So how do you do that? Is you first try to find P. So we start from here, we begin our access until we reach the pointer P, correct, which is here. So we keep on, so we start from the header, check here, we find that the data is P, after this which x has to be inserted. So we first create x, then we locate P, and then simply readjust the pointers. So what we do is, recollect, we have this node has to be inserted in. So we point precisely, use this previous pointing to this, then we will look at the next, point to this, the next of this is going to point to this, and the previous is pointing to this. So what you do is you first create a node that which you have to insert, store the data that you want to store there, traverse up to the point where you want to insert, and simply update the pointers. By updating, so what you do is you simply, in this particular case, you are going to remove this pointer and update them to, this pointer is going to point to this pointer is going to point to to this. So it is just updating pointers. So insertion is traverse up to a certain point, create that particular node which you want to insert, and then simply readjust the pointers. That's a simple insertion algorithm that we have. It's a pseudocode again. So as we said, first create a new node V where you want to store that element E. Right? So the first step is to create a node, and then you're going to traverse to this. So you traverse up to this, and then simply adjust the pointers. Right? So the algorithm precisely tells you that. So as we said again, this is abstraction. So it just tells you how you're going to achieve this rather than how we are going to achieve it. So how we achieve is create a new node, traverse to a point where you want to insert it, and simply adjust the pointers. It is again easy to observe that all these operations, adjusting pointers, are independent of the size of the list. Your list can have any number of elements, but adjusting it, right. So if the adjusted part which is done here is local, which is just adjusting the next and the previousness of this three particular nodes. So it precisely takes a constant time. Right. So adjusting pointers just takes a constant time. So this particular adjustment takes you only a constant time. The time required is the time to traverse to that particular node. So if you look at the traversal time, it is proportional to the number of nodes that you are going to traverse. Adjustment of pointers is just going to take you a constant time. Similarly, deletion algorithm, suppose you want to delete a particular node, you first need to traverse to that particular node and again adjust the pointers. So the next of this will be pointed to the next of this, and the previous of this is going to be pointed to the previous of this. Right? So it is just pointer adjustments once you reach that particular node. Once a node is linked out of the queue, this can be collected by the garbage collector, and that space can be made available. Yeah, so that precisely is an algorithm for dequeuing. So you first traverse to that particular element and then simply adjust the pointers. Again, pointer adjustments will take you only a constant amount of time and not which is going to be independent of the number of nodes that you have into a list. So in a doubly linked list, insertion or at head or tail is going to take you a constant time. Insertion at any other points will take you a linear time. The linear time is going to be needed because you have to traverse to that particular point and then do your pointer adjustments. Right? So as we see that linked lists are a good option when we have no idea beforehand about the problem size that we are going to deal with or the data that we are going to handle. Arrays are useful when you have a precise idea about the data that you are going to handle. Then the access is fast. Operations that you perform, enqueue, dequeue or push pop, are also efficient. But when you have applications where you have no specific idea about what size of data you are going to handle, it's useful to use linked list, though the operations now happen in linear time rather than constant time.